motion becomes a movement. And so the experimental results, what does it look like? We saw the movie itself, but again, like any other good type of blockbuster, there's a CG involved. You got to run a computer. So in this case, the signal that we measured, and in that measured signal, it doesn't look like a molecule at all. And so if you look at through time, how the X-rays scatter on that big Tetra detector, the X-ray can't work. As we saw those rings, the positions of those rings, like I said, it's very meaningful. If you just looked at all the signal on that detector, it would change through time and give you a funny shape like this. So the flat line was when it wasn't excited, and then some time delay later, the X-ray takes a picture, and that pattern is changing. Look at that again. But what is that change? What is this telling us? These kind of wiggles go from a flat line to some type of wiggling pattern. Well, in each of these little slices in time, we have over 10,000 individual frames. So there's some have more, some have less, but on average it's about 10,000 shots. And each time step that we were able to bin it down to, like the smallest time that we can look at, is about 25 femtoseconds. So in each of these 25 femtosecond slivers of time, we have about 10,000 X-ray shots. And then what we plot here is the average of those 10,000 shots in any given time. And this is kind of what you see as this molecule, as the structure, the component that you measure on the detector changes. Well, these wiggles that we tell you about, something goes up and something comes down and something goes back up, these wiggles are very, 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 very meaningful. They tell you something about where the atoms are in relationship to the electrons and all this other good stuff. And as you can tell where the electrons go, the atoms aren't very far behind. So it tells you something about the structure. So these wiggles are actually meaningful because as this molecule opens up,
ここから 9.9 キロだ。めっちゃやな、これ。めっちゃ遠いやん。和田小屋。上まで10キロ。和田小屋まで10キロ。
But they all play together and they all interact together. So what happens is they become smeared out a little bit. And so, but we have to try to tease out how that smearing occurs. To get all these interactions and try to know them by heart and how it best fits and represents the molecular structure that we see on our detector. Well, we need to optimize this. This is where our slick CG comes in. And so we have all these tens of thousands of shots that we look on the detector. And if we want to model each of these snapshots and see what the molecular structure actually looks like. And so when we compare it to the experiment to the theory, this is what we see here. We calculate the bond distances between the bond that breaks when it got excited by the ultraviolet laser pulse, and we watch the distance of these atoms move apart. And this is this axis here. And so we tell the computer, monitor these 2 points, here's some energy, go. And we let the molecule do its thing. And we do this for many, 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 many thousands of events. And so we see all these different trajectories, and all we're saying is each of these are kind of the molecule, because if you go across one line versus another line, there's a distance. But what does that look like in the picture that you're trying to see? If you were to walk across one of these lines,
渓流です。
What is the path this molecule can take to look like our detected signal. That's the most interesting one. That's the one we're measuring. Again, there's a little bit of error bars. We'll get to that later. But here we go. We spit one out. The computer said, voila. CG happened, and we found that if you can kind of see, compare basically, this is again what we measured on the detector at LCLS, and this is what we kind of computed. Well, it turns out that it's basically a little bit of a mixture of some predominant trajectories. And these trajectories are these lines. And if you distill how, if you let these molecules go, you tell it, excite, boom, unravel, and see what happens. These molecules tend to go on these bigger, darker lines. These darker lines have more weight, more probability. There is more chance the molecule is going to follow these paths. Open up. You also notice that that can't happen. It's a quantum mechanical system. Crazy things decide not to open, not close, open, we all do it back again. And it actually does. You can kind of see some of the trajectories. And so about half whereas the other about 30 or 40% don't open. But all the small dashed lines do mean something. There's about 5 to 6% probability, chance in each of those lines that the molecule will open. And you see that all those dashed lines, they tend to, the molecule goes open. And so it could technically follow one of those paths, theoretically. And so the ratio of which was an outstanding issue. If you looked at some liquid chemists, or organic chemists, they would say, oh, it's about half. Interrogate molecules with lasers, we would say it's about 90% of the time. I believe it's still 90% of the time because other type of spectroscopic measurements using optical lasers say so. And I can tell you how we can try to solve that problem, and we really come to some closure a little bit later. But we can look at each of those little trajectories, those blue, purple, red, and yellow trajectories, and these are what the molecular structures are doing as you walk across those lines. As this molecule opens up, closes back down, and this is what we're saying. These are routes that the molecule can actually take. The one that we actually see that you saw kind of the surface on was closer to that. Was closer to the purple one. That was the closest to what we have measured.